Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, grade 9. This is a quick recap for chapter 1. In the first part, I will talk about the number systems. So I will just revise the conversion between the different number systems, how to convert from Denary to binary, from binary to Denary, and from binary to hexadecimal, from hexadecimal to binary, and from Denary to hexadecimal, and from hexadecimal to Denary. Then I will give a simple example about the binary addition, the bit shift, and the two's complement. This will cover the first part of this chapter. So let's begin. Okay, if I want to convert from Denary to binary, suppose that we have this binary number 200, let's say. Okay, and I want, Denary number, I want to convert it into binary. So we have two ways to do that. The first way is to write the headings of the base 2 headings of the binary numbers. So we can write 1, 2, 4, 8, 16, 32, 64, 128. Okay, 256 is not needed because 200 will be less than 256, so it's okay not to include it. Okay, now 200 is greater than 128, so we put 1 here, then we subtract 128 from 200, so 200 minus 128, so we get 72. 72 is greater than 64, so we put 1 and subtract 64 from it, so we get 8. Okay, so 8 is not greater than or equal to 32. Okay, so we put 0 here, and it is less than 16, so we put 0 here. Okay, 8 so equals to 8, so we put 1 and we subtract 8, we get 0, so the rest of the numbers here will be 0. So we get this number 1 1 0 0 1 0 0 0. If you want to make sure of your solution, just add the headings, okay, the headings that are corresponding to 1. Okay, so you will get the result. So if we say 8 plus 64 plus 128, so 8 plus 64 we get 72 plus 128 will equal 200. The second way of converting Denary number into a binary is by successive division by 2 until we reach 0. So we write the number 200 here. Okay, so we divide it by 2 and we need to record the remainder. Okay, so anything divided by 2 will give us a remainder either 0 or 1. So 200 by 2, it will give us 100 and the remainder will be 0. We must write the remainder. Okay, 100 by 2 will give us 50 and the remainder 0. 50 by 2 it will give us 25, the remainder is 0. 25 by 2 it will give us 12 and the remainder will be 1. Okay, 12 by 2 it will give us 6 and the remainder will be 0. 6 by 2 it will give us 3 and the remainder is 0. Now 3 by 2 it will give us 1 and the remainder is 1, and 1 by 2 will give us 0 and the remainder is 1. Then we write the numbers from bottom to top. Okay, so we write the number 1 1 0 0 1 0 0 0. So this is equivalent to the number 200 in Denary. In the exam you can use the way you prefer. Okay, now how to convert from a binary number into a Denary number. Okay, let's just clear the canvas. Okay, from binary to a Denary number. Suppose that we have this binary number, let's say 1 1 1 1. Okay, 0 0 0 1. Okay, so this is an 8-bit number. I need to convert it into decimal, it's very straightforward. Just write the headings, the base 2 headings. So 2 to the power of 0, which is 1, 2 to the power of 1, 2, 4, 8, 16, 32, 64, and 128. Okay, then add the numbers that are corresponding to 1 together. So we have 1 plus 16 plus 32 plus 64 plus 128. So how much we get? 17 plus 32, 49 plus 64. We will get 113 plus 128. Okay, if I write it here, 113 plus 128, 142. So we have 241. Okay, if so, this is the value, the Daenery value of the given binary number. Now, if I want to convert binary number to a hexadecimal, you need to know that hexadecimal uses 16 digits from 1 to 9. Okay, let me just here canvas. Okay, so in hexadecimal, okay, usually we write hex. Okay, from 1 to 9 and from A to F. A means 10. Okay, B 11, and so on, and F equals 15. Okay, so you need to know that each hexadecimal digit, okay, represents 4 binary digits. For example, the number in the previous example, okay, if I write it 1 1 1 1 0 0 0 1, okay, which is in Denary 241, but we are not going to convert it to Denary. This time we are going to convert it into hexadecimal. Okay, into hexadecimal, you know the values of hexadecimal. You can refer to the table that is in the book, or you can just calculate them or find them. So this will be number 1 in hexadecimal. Okay, and this will be the number F, okay, or 15. Okay, 15, which is F in hexadecimal. So we get F1. If you don't want to memorize the table, you just convert them to binary, each 4 digits. For example, 1 2 4 8. This will be simple to you. 1 2 4 8. Okay, and add the ones. So here we have only 1. And here 1 plus 2, 3 plus 4, 7 plus 8, 15. 15, which is equivalent to F. So we get this number. If you want to do the reverse thing, just you take each hexadecimal digit and represent it by 4 binary values. Okay, so this, it's not like a real conversion, but like change the way we represent the numbers. Okay, so 1 will be like this, 1 0 0 0, and F will be 1 1 1 1. Let's take another example. For example, let's say A 3, let's say. Okay, so we take A. If you go to the table, you will know that A is, okay, equals to 10, or in binary we have 1 0 1 0, and 3 you have 0 0 1 1. If you want to make sure, just take each, okay, each 4 digits. Here we have this 1 2, okay, so we have 3, and this one we have 1 2 4 8, so we have 2 plus 8 will be 10, which is A in hexadecimal. This is very straightforward. Okay, now how to convert from Denary to hexadecimal and from hexadecimal to Denary. Okay, it is similar to the way if I want to convert from Denary to hexadecimal. It is the same way that I convert from Denary to binary, by successive division. okay, but this time on the base of the system. The base of hexadecimal system is 16, so we will divide by 16. Suppose that we have this number in Daenery, let's say 122. Okay, I want to convert this into hexadecimal number. Okay, so the first thing I need to divide it by 16. Then we need to record the remainder as we do in converting from Denary to binary. Okay, so if we say 122 by 16, it's better to use the long division. Okay, 122 by 16. Okay, so if we get 8, okay, if we write let's say 122 by 16, we will get 7. 7 by 16, we will get 12. So we will get the remainder 10 here. Okay, so 16, 10 doesn't go to 16, so it is the remainder here 10, and the result here is 7. Now 7 by 16, we will get 0, and the remainder will be 7. Okay, and we write them from top to bottom. So we write 7, and the letter that is corresponding to 10 in hexadecimal, which is A, okay, is written here. So we will get 7A equals to 122 in decimal, okay, or in Denary, sorry. If I want to convert this number back, or if I want to make sure of my solution, just we need to put the headings, okay, so and multiply each number by its heading and add them to each other. For example, the headings here for base 16, so we begin 1, 16, okay, then every time we multiply by 16, okay, so if we have more digits, but for this we have A, which is 10 times 1 plus 7 times 16, okay, so 10 times 1 will be 10, okay, plus 7 times 16, it is 112, 112, so we get 122. Okay, now how to convert hexadecimal number to Denary number? Just write hexadecimal number. Okay, let's say 1 3 CA, let's say. Okay, we need to write the headings of them, the base 16 heading. Okay, so we have 16 to the power of 0, which is 1, 16 to the power of 1, 16, 16 to the power of 2, 256, okay, and 16 to the power of 3, okay, which is 4096. Okay, so now we add the corresponding value to A is 10 times 1 plus the corresponding value to C, okay, which is 12 times 16 plus 3 times okay, sorry, 3 times 256 plus 1 times 4096. Okay, so we have 10 plus 12 by 16, how much we get? 32 plus 160, 192. Okay, plus 256 times 3, 768. Okay, 768. Okay, plus 4096. Okay, so we add them together. So we have 202. Okay, so we have 202 plus this 0, 0. Okay, 7, 4 plus 4096. Okay, 4, 7, 0. So we add 6, Okay, 9 plus 7, 6 here, 5 and 4. So we have the 4566. Okay, if you want to convert it back to hexadecimal, we just do a successive division by 16. Okay, so far we have learned how, or we have revised how to convert between the different number systems. Okay, now I'm going to talk about the second part of our topic, which is the binary addition, how to add two binary numbers. Okay, and it is very straightforward. Okay, so to add two numbers together, two binary numbers, it's a very simple addition. Okay, just you need to be aware of the overflow that might occur, okay, or that we might have. So suppose that we have these two numbers 1 1 0 0, okay, 0 0 0 1, okay, plus, okay, this number 0 1 1 1 1 1 0 0. Okay, so it's very straightforward. This 1 plus 0 will give us 1. 1 plus 1 is a 0, and we have overflow 1. Okay, 1 plus 1 is a 0 and overflow 1 here. Okay, 1 plus 1 we have 0 and the overflow 1 here. 1 plus 1, okay, 0 and the overflow 1 here. 1 plus 1 0 and overflow number here. Okay, 1 plus 0 plus 0, it will be 1, and 1 plus 0 will be 1. So we'll get this number. Okay, now let's talk about the bit shift. Here we have two, we can shift the bits either to the left or to the right. If we shift the number to the right, okay, so we add a 0 from the left side, okay, and this will result in a division by 2, okay, and if we shift it by to the left, then this is equivalent to multiplying the number by 2. We add the 0 from the right side. But you need to be aware that we have a limited number of shifts, because after a certain number of shifts we might get a wrong result, okay, or incorrect result. So suppose that you have an 8-bit register that contains this number. Okay, let me just draw the register 8-bit numbers, okay, or 8 numbers. Let's say 0 0 0 1, okay, 0 0 1 1. Okay, so if I want to shift this number to the left, and this will result in multiplying the number by 2, so I will have 0 from this side, okay, so 0, and the rest of the bits will be shifted. So the last 0, the leftmost 0 will be out of the register, okay, so you need to be aware of this. So we will have 0 1 1 0, okay, 0 1 0, okay, just wait, we put this, okay, 0 1 0 0, okay, so we have this number. If you look at this, this is the same number but multiplied by 2. So if I put header 1 2 4 8 16, let's say 32, okay, so this number will be 1 plus 3 plus 16, which is 19, okay, and this number will be 2 plus 4 6 plus 32, which is 38. If we shift it one more time, okay, so we have 0, okay, and 0 1 1 0 0 1 0, okay, this number will be the double the previous number. Okay, so each time we shift the number to the left, okay, it will be multiplied by 2. Okay, but if we shift it 2 times more, we will get a incorrect answer, because the 1 will be out of the register size. Okay, same thing we do when we right shift the number. Any number you shift it to the right, this will result in the number divided by 2. For example, if I have 1 1 1 1 1 1 0 0, okay, so if I add a new 0 from the left side, okay, the number will be 1 1 1 1 1 1 0. Okay, so the last 0 will be out, the rightmost 0 will be out. And if you look at the number, this number is the half of the first number. Why we need the bit shift? It's faster for the CPU to perform shifts rather than doing or performing a multiplication, the traditional multiplication. Now we will learn how to represent the negative numbers in binary system. Negative numbers in binary, we don't have the sign positive and the sign negative. Instead, we use 0 or 1. 1 means negative and 0 means positive. Okay, so we have something called 2's complement format in order to represent negative numbers. What is the difference between the 2's complement format and the format we've learned before? Is the last or the leftmost heading. For example, suppose that I want to represent the number 79 using the 2's complement format. I need to put the headings 1 2 4 8 16 32 64 128. Okay, 128. We need to make a small change to the last heading. We make it in negative. So now if I want to represent the number negative 79, what should I do? I will just subtract this number from 128. Okay, so I will get 49. Okay, now since the sign is negative, so I will put 1 here. Okay, then I will represent the number 49 here. So 49 here we will have 0. Okay, so 49 is greater than 32, so we have 1, and we say 49 minus 32, we get 17. So we have here 1. Okay, and 17 is 16 and 1, so 0 0 0 1. Okay, so this number is equivalent to negative 79. If you want to make sure, just add the headings that are corresponding to 1. So we say 1 plus 16 plus 32 plus negative 128. Okay, so we get negative 128 plus 49. Okay, and this equals negative 79. The other way, if I want to represent negative 79, I can represent the positive 79. Okay, so we can write the headings 1 2 4 8 16 32 64 128. Okay, and I want to represent the positive 79. Okay, so in this is the first step, so we put 0 here, then 1, so 79, we put here 79 minus 64, we get 13. 79 minus the, yes, we get 13, sorry, 15, 15, okay? Now, here we have 0, we have 0, here we have 1, 1, 1, 1, yes. 1 plus 2, 3 plus 4, 7 plus 8, 15, okay? Now, this is the number 79, okay? How to make the 2's complement, okay? Here we have the 2's complement format, so we should keep the leftmost in negative. This is negative 128, not 128, sorry, okay? Negative 128. Okay, now we need to switch each 0 to 1 and each 1 to 0, okay? Then we will add 1. So this is 1, I will switch it to 0. 0, 0, 0, this will be 1, this will be 1, this will be 0, and this will be 1. Okay, did we finish? Not yet, okay? What should we do? This is the 1's complement. If in order to get the 2's complement, we will add 1, and the result we will get will be the negative value, which is negative 79. Okay, so this will be 1, 0, 0, 0, 1, 1, 0, 1. Okay, so this is equivalent to negative 79. Okay, that's it. I will make another video for the other topics, inshallah. I hope this is understood, okay? And stay tuned and try to do your best.